branch, I'd like to introduce Thomas Clifford from Gears and Oliver Kibble from Tarmac. So they're going to present to us today some groundbreaking technology that they're working on, looking at the use of AI in blasting. And for the work they've done, they've also they've won the Emerald Award in 2023. So without further ado, I'll hand over to Thomas and Oliver.
Thanks, James, and yeah, thanks to Devon and Cornwall for hosting us today. I'll let you kick off then, Oliver.
Perfect. So good afternoon, everyone. Yeah, thank you very much for joining and taking the time out for our presentation. So just an introduction to myself, been within the industry now for 6 years working for Tarmac. Started off as a general management graduate on the graduate programme, then progressed into a shift manager role at Whitwell Quarry in Derbyshire, before taking on the quarry manager role at that location, and then more recently coming into the quarry development manager role at Mountsorrel, which you can see there in the background, and taking on the process engineer role over the last few months at the site. So a bit about my background in education. So I took on the Derby University Mineral Extractive Studies as a diploma student, and prior to that I actually studied history at Nottingham Trent University and taken on various other industry specific training, and you see a couple of the awards there in years so far. And as we come on now to the project, so the reason for the Blasting Down CO2 project is the UK mineral production is the largest UK industry by volume. It's worth £16 billion per annum and supplies the UK industries with over 600 billion in combined turnover. So we know the UK annual aggregate production is 190.5 million tonne, and 125 million of that is crushed rock. So looking at the energy consumption, using over 2 billion kilowatt hours of energy per annum, and that equates to 45% of the production cost. So there's massive opportunity there, which we'll come on to how we're focusing on it, and that converts into 588,000 tonnes of CO2. So of that figure, the hard rock quarries specifically, which we'll be focusing on today, equate to about 388,000 tonnes of CO2. And we know that poor fragmentation and inefficiencies in crushing operations can contribute up to 136,000 tonnes of that based on the research carried out. And the inefficiencies contribute to 10% waste and 17% fines within the process. And it's costing our industry £776 million per year. So as part of the Emerald Challenge, we tasked to look at how we can reduce the CO2 inefficiencies, and the opportunity that we've found so far in the process is around 77,000 tonnes of CO2 from the hard rock quarry specifically. So we'll talk you through this process flow. So initially starting off at the very start of the process, looking at the actual blast design and how we measure the vibration control, review vibration prediction, the density of the rock and the load and haul processes. There's a 31,000 tonne CO2 opportunity there for us to focus on. As we then go into the oversize, so after the blast, looking at secondary breakage due to the ineffective blast designs and how that has an impact on the CO2. So again, in this specific area, around about 11,500 tonnes of CO2. So just on this image below, this is one of our development areas that we've looked at as part of the process. You can see there just the cost of the oversize. So you have one excavator on load and haul operations, you then have the oversize in the middle, and then on the left-hand side you have the breaker. And it's just all of this additional cost and inefficiencies in fuel burn, operator and man hours, and the oversize that slows down the throughput and production. So as we look at the blast design process, we know combined there's 42,724 tonnes of CO2. So you can see this just shows at each stage of the process the significant potential in CO2 savings and how we can be more efficient within the operation. So coming on to part of the tools and software that we've developed in partnership with Gears, is one of the first parts is FragMap. In this image here, on the right hand side, you can see the overlay of the software, and this analyzes the fragmentation size of the blast pile. And the image in the background is actually one blast. So you can see on the left hand side the significant oversize, and then the software overlaid on the right just to compare and this is a really key part of what we've used to optimize our site and really demonstrate where our inefficiencies are. So this is the software in action, if you like. This is one of our early stages. So within the blast pile, we can circle a set area of the entire blast. The software then picks out the oversize in different colors based on what you enter into the system. So you can target your ideal size for your crushing operation based on what crushing plant you have on the site. And the software then runs using AI and machine learning, which we'll come on to later, to analyze the oversize within the pile. So you can just see there, it's really clear where the oversized pieces are and how that will have a knock-on impact in CO2 within the process. So post-blast, we have the processing part of the operation. So this is where we know there's a further 34,954 tonnes of CO2 potential usage of CO2 within the operation, and we're utilising an AgCam software, which we'll come on to explain, to really optimise the process. So what AgCam is, it's a camera that we've installed, initially a GoPro camera, as our first prototype project. It sits directly over the conveyor belt, which is our first conveyor after the primary crusher. So this sits there and can monitor, take a photo every 5 seconds, and that then records and processes the particle size on the conveyor belt. So on the far left, you can see the camera just sat just above, all powered through, taking the photo through and all calibrated using belt cuts to ensure accuracy. And then you can see the image that's being taken, and then different images it's processed through, again, just highlighting out the particle sizes so we can set our crushing operations to be the most efficient and really optimize the process. So this is the data and the information behind the AgCam. So you can see there the highs and lows and where we have oversized particles coming through, and that's all based on our percent passing and our max tolerance for what we want through our secondary processing plant. We can really optimize our crushing setup. And what you'll also notice there is the low points where the conveyor belt's actually running empty, so we know that there's an opportunity there for improvement. And as a result of this software being in place, in combination with our other telemetry, we're able to identify where we're not getting the required throughput through the crusher for whatever reason. So what we've then focused on was how we can be more efficient, not only in terms of fragmentation, but also site setup and our fleet that we use on site as well. So we focused on Mountsorrel. This is where the project's been ongoing and links to the Emerald Challenge. So we chose Mountsorrel as the scale of the operation and from the deepest quarries in the UK. And it's recently had a new primary crusher installed. And that's up to 2,500 tonnes per hour. The ThyssenKrupp gyratory crusher. We've got new plant on site, including the 6030 face shovel, a fleet of Cat 777 rigid dumpers, and we've also got the ability to track the telemetry and information and statistics at every stage of the operation, so we can really focus on how we're performing and improve the operation, which in turn we can then use to reduce the CO2 impact and associated cost savings as well. So, like I say, it's one of the largest quarries by production tonnage in the UK, and that enables significant CO2 and cost savings, exceeding the smallest of savings applied across the tonnage throughout the year. Yeah, has a significant potential. So, as I said before, we're using state-of-the-art AI and machine learning software, which has been developed as part of the Emerald Challenge through the Institute of Quarrying, and we're measuring the entire mine-to-mill efficiency of the operation at Mountsorrel. And the aim is that utilising Mountsorrel as our initial test area, we can then branch that out to other sites at any sort of scale and level. We've also got a really engaged workforce, and we've really had to involve everyone at every stage of the process to be able to get everyone to buy into this project and why it's so important. So our initial aim with the Emerald Challenge was using Mountsorrel as our initial test site and to determine if the enhanced blast fragmentation would reduce the CO2 emissions. So our initial objectives were to measure the following from a typical blast. So that gave us our baseline results. So what we did from there was look at the blast pile fragmentation, the average dumper load and output, primary crusher energy usage, the fragmentation, which is tracked on the AgCam, which we just discussed, and the dumper and excavator fuel consumption. We then looked to vary the blast design and remeasure just to determine how different factors have an impact on the CO2. So we've analysed the data and we've prepared a summary project, which was submitted to the Institute of Quarrying, and it's also been published in the Quarry Management magazine as well. And as part of this is presenting our findings. So yeah, thanks so much for running through where we're at so far with the project. So I'm going to run through now an example of the blast analysis that we've run. So this one particular blast, it was 50,000 tonnes. This based on the belief that larger blasts are cheaper, and we just wanted to really start to increase our blast sizes to see how that had impact on the CO2 use and inefficiencies on the site. This particular shot was in a confined bench in the development area, had multiple rows, and based on increasing the blast size up to 50,000 tonne, presented an approximately £1,000 cost saving based on standard designs. So what we actually found when we ran the analysis, in this particular location, we identified significant breakback, and the software, once filmed using the drone, identified significant oversize within the blast pile. This is an example of one from that exact blast, and you can see there the particle sizes that are increased from our standard size. So we then ran this through the software, and this is where we can really see the impact of the block size within the shot. So we compared this, you can see the trend line across two of the previous blasts, going into our oversize, so based on our optimum sizing for our crusher, which we determined at 1,000 millimeters, and then our percent passing throughout the blast. So you can see relatively similar for those two standard blasts. And then when we actually ran this particular blast through the software, you can see there that we've got the increase in oversize as well, which you can see was actually a 10% increase in oversize on the previous two blasts, 230% increase in the 50% passing point, 300% increase in secondary breakage post-blast, and that was actually led to a 700% increase in breaker arm time. So at Mountsorrel, we have a breaker arm within the primary crusher. Any oversize that gets to that point can also be broken down using the breaker arm, and that increase, 700% on standard operations. So you can really see at each point is having a significant impact across the blasting operations and our efficiencies. So at every stage there, we have potential for trucks to be waiting, standing time, reduced throughput, plant idling, and all of these areas impact our CO2 use on the site. So as a direct result of the poorer fragmentation that we found in this particular example, we found a 15% increase in CO2, and that's obviously an area that we want to reduce and focus on, and a 7% increase in costs. So it just shows how the difference in the varying number of factors from geology to blast size to location can all impact on not only the CO2, but the costs as well. Perfect.
And then over to me.
Over to Tom. Thank you very much.
So yeah, thanks, Oliver. Obviously, Oliver's given insight into what's happening at Mountsorrel, and it's been a really good journey. Now, from a gears point of view, we're basically an independent consultancy. We're a very small team, but we work with a company called NewGradient. We're on a joint venture with them, and they are experts in artificial intelligence and machine learning. So with them, we've basically been developing these software solutions that Oliver's been showing you. So Before I kind of go into what we've been working on and how it all fits, and I suppose it's enabled Oliver to do what he's been able to do at Mountsorrel, I'll just quickly explain my background. I used to work for agri-industry, so I started off my career as a geologist and geotechnical specialist at AI. I was there for about 10 years. I then left to focus more on the engineering side of things. So I joined this massive consultancy called Atkins, owned by SNC-Lavalin. So they're one of the biggest mining consultants in the world. And I got to spend an awful lot of money on developing the technical understanding around blast vibration and really do some in-depth research into that, which I'll talk a bit on later. I spent about 10 years with Atkins, and then Paul McMillan, who set up Gears, invited me to come and join Gears and really develop this software solution. Paul's background is he used to work for TRL, which is the Transport Research Laboratories, and about 15 years or so ago, he was working with Tarmac, looking at blast optimization, and then rolled, 3 years ago, he re-looked at where we were in the world of blast fragmentation, and I think he's kind of seen that, or his view is that we've kind of gone more contractor-led. Back when I was with AI, we had quite a few in-house teams, in-house experts. It's now moved over to be more kind of contractor-led, so it kind of feels like we've lost a little bit of knowledge within the operator side. So Paul wanted to set up a system to help operators kind of have a bit more technical knowledge, some systems that can track KPIs, work with the contractors. And I think one of the big changes over the years is there's been a real drive to reduce the cost of drill and blast. And most operators are looking at cost in silos. So drill and blast is one cost, and the drive is to drive that down. But we all know that has then a knock-on effect on all the other operations, which Oliver's quite well explained in terms of the impact on Mountsorrel. So we developed this this mine to mill concept, which looks at the full cost of the operations we're doing. Now, traditionally, mine to mill has been looked at. You start off at drill and blast, and you work all the way through to your final product. But what we realised was this is more of a cycle. Actually, what decides your drill and blast is going to be the market. You need to look at your products first, and then we can start designing the drill and blast solutions around that. So from my kind of ops kind of background, I could then apply my training as a geologist and also as an engineer. And it's got a couple of degrees and things behind me. But that then gave us kind of really the technical understanding to start driving this through forward. And I suppose from our point of view, we are looking at this very much from the kind of geological geotechnical specialist input onto this. And there's really good blasting contractors out there who can lead on the blast design element of it. So we're kind of trying to add something a little bit different or next level on it. So that's the mine to mill. So if we kind of put everything together as Oliver's gone through, and you look at that final cost or the quality of what's being produced, that's the mine to mill, and that's a system that we're in the process of developing. But in order to get there, we've kind of broken it down into various different bits of software, which you can see along the bottom. So the first part of it is we've got an advanced program that looks at the geology in a lot of detail, looks at the market, and it kind of works out what potentially is the theoretical optimum blast design. And we've done a few trials of that very successfully up in Scotland. But the main programs that we're talking about at the moment is two. We've got a massive project called Project Blastwave, and that's probably going to turn into a bit of software. So just to give you a little bit of background about Project Blastwave, it's taken over a decade to compile all the evidence, but we think it's probably the most comprehensive engineering assessment into quarry induced blast impacts. So this is looking at air overpressure and ground vibration. Because of the work that Paul and I have done on the civil side, I mean, I've done studies of looking at the blast impact next to live nuclear power stations. So we've had multi-million-pound projects really go into detail in this. So we can take that technical understanding and basically bring it back to the quarrying industry. But what's been really critical for us is over the last 3 years, and it's probably about 3.5 years, we've been in partnership with Tarmac to really kind of develop this and hone it, and hopefully you can see some of the results coming through from Mountsorrel. So today's not talking about Blastwave, but the Mineral Products Association have asked me to do a bit more of an in-depth presentation on Project Blastwave. So that's on the 19th of November at 10 AM. So apologies for the plug, but if you are interested in the impact of blasting in terms of vibration and air overpressure and what we're potentially going to be looking to change and adopt in the future, then please come and join us for that presentation. So that's Blastwave. The next part, as Oliver's touched on, is FragMap. So this is the analysis of the blast pile. So I'll just basically show you a video of the actual program. So on here, we've got various different quarries in there, and we can set up a new project. So this is putting together the blast that Oliver was just talking about at Mountsorrel, the 50,000 tons. And in there, we can set the fines and the oversize limit on there. And we can put in the blast parameters on here as well. And that just keeps a basic record of what's going on. Now, within the software, there's a couple of major limitations when you are analysing a blast pile, because you're only looking at the surface of it. So we've developed a kind of a new approach to it, and that is for some blasts, as Oliver showed, you can have the stemming zone can be very large, but it's just sat on the surface. So we do two assessments of the blast pile. We do, should we say, the characteristic. If you pick apart the blast pile that looks kind of representative of what you're going to be digging through, and you don't have to do this straight away. You can collect the drone imagery, you can dig into the pile, but basically you go and identify an area that you go, right, that's nice and representative of what's happening in the blast pile. Now with the stemming zone, where you've got the core stuff at the top, you can then draw a second field. And what it does, it brings the stemming zone field, because that's just on the surface, against what's typically happening in the blast pile, looks at the areas involved in the tonnage and brings the two things together. So you can see here, it's just running on the right. This is an example of one we did up with Bam Ritchie's and Tarmac up in Scotland. So hopefully it's playing through a video, but hopefully you can see the quality of the analysis that's going on. So we don't know of any other system that's operating to this kind of level of detail. Most systems that work out there use what we call a mesh function, and it has to put basically loops around everything that you've got in there. But with blast piles, you've got to look at everything individually, and this is where the artificial intelligence comes in. So it does the analysis, and you can see on here basically it produces a grading curve for you. So for the blasting contractors and the operators, we've got what we could almost call as like quick KPIs. If I just go back on the left hand side here, so for this quarry, they've set the fines at 125 because it's a low value product. Once it goes into like an MOT material, the value here is on the 14 mil. So on here, we set the fines, and so they're running about 30% fines on it, which they know. And this is where we can look at changing the blast design to try and reduce the amount of fines being produced. You can see on here, the average size, it's actually really quite fine. It was deliberately blasted that way. And what we're looking on here is you've got a 6% oversize. So you can get some really quick KPIs out. Now, that helps both the operator and the contractor, because when you're talking about pence per ton, actually what we can now do is kind of independently assess it and go, right, well, yes, we can reduce the pence per ton, but these quality metrics, they're going to be impacted, or vice versa. On here, you go, actually, we could probably go slightly cheaper and take something slightly coarser, but at least we can talk about the impact on quality. So, as I said, it's doing a couple of different analyses in there. It uses this artificial intelligence engine. Now, in order to process Oliver's 50,000 ton blast, we calculated the amount of processing time and cores was used to do it. So to run it, it has to run through a supercomputer. It's equivalent, that analysis is equivalent to running 2,500 laptops for an hour. And that's how it basically operates. So once the data comes in, it goes off to a supercomputer. We rent it off Amazon, and it then processes through there. And because we basically do everything in parallel with lots of different cores, it can take up to about an hour to process it. And then it brings all the data back together and streams it from there. But the final output from this is a grading curve that you get. Now, it is just the blast pile, and it's the surface of the blast pile. Now, you could go and dig in the blast pile and then fly again and try and look at the inside of the blast pile. But however you do it, you're only able to sample what you can see. So whilst the accuracy of this clearly is very good, we are just taking the surface representation. Now, one of the challenges then is, whilst we can go to quite a fine size because the way we fly it, and you can see how well the AI engine works to detect the blocks, there is a limit. Once we get down to about 10 mil, it doesn't matter how good your camera is, it's kind of under the blast pile. So to make the bottom end of the curve, we've been really lucky. A prof out in Sweden had collected loads of data, and it was one of the largest blasts tests that have been done in the world, and they actually physically screened the whole blast pile. Now, there was a couple of things that came out from that work. One was we got a huge data set, and because he was retiring, he very kindly gave it to my MD, Paul Macmillan. So we had this huge data set of properly sieved blasts, and he built like an idealized gradient curve. It's called Swebrek. But we've then further developed that and used it within our system. So even though we haven't got, say, the 10 mil down, we can actually project that by using this data set. It can basically rebuild that curve. So it can look at the shape of the curve and then do that forward projection. So there is an element of projection in there. So the next challenge is, well, we're still looking at the surface. How can we do that kind of quality assurance over it? Now, some of the users are kind of like, well, it doesn't really matter if it's not perfect. What's important here is it's repeatable. And the front of the blast pile is likely to be the coarsest part of the blast pile. So actually, it's a nice conservative measure. And if we keep repeated surveying the front of the blast pile, at least relatively, we're seeing the change. But we kind of wanted to get more data through the blast pile. And that's where we pushed on to the AgCam system. So with the AgCam system, as Oliver's shown you, we wanted to develop the technology. So should we say it's targeted at quarry pricing, not mining pricing. So the challenge was, could we take this software, this AI engine, and apply it to a GoPro? And that was a challenge at Mountsorrel, and clearly successfully we did. Now the camera we're using now is a little bit more advanced than a GoPro, but I think they're about 4,250 quid. So I mean, this GoPro was £1,000, but that's now it's got 2 lenses on it, so it's got full depth maps and it's all integrated. But the point is, we can get basically a very cheap camera set up, and we can then run it through some really advanced software. So whilst we're very comfortable we've got the quality sorted, the critical thing for us in the quarrying industry is it needs to be cost effective. I would like to think that we've hit that brief as well. But the idea behind the GoPro is we wanted a system that could be pretty well deployed anywhere. So with a GoPro, we can put it on the back of the dumper. You could put it on, say, the primary, and so you could look at dumpers tipping off. You can analyze it there, or as shown here, we can look at it along a conveyor belt. Now, one of the challenges with this kind of system, and this is one of the reasons we set it up here, is that conveyor belt that's moving at what? Is it, your primary is doing 2,500 tons.
Yeah, the conveyor's over 2,000 tons per hour.
Yeah, so it's not a slow moving conveyor belt. So with the camera technology, we were able to get it so we can take photographs very quickly. Now, with the new camera setup and the way the software works, we think we're down to about taking an image every second, which means the primary operator then can have a live feed of what's coming through. And what was really exciting to us is we were looking at this from, okay, we understand what's happening with the blast pile, what's happening within the crushing plant. Let's look at the grading curve. But what was the kind of the first feedback is when it was set up and Oliver was running it, you saw that video where a lot of the time it was just running with nothing on it. And Oliver kind of rang us and said, well, this is the data, let's have a look at it. And we were like, oh no, the system's not working because it's not recording anything. But the good thing is we had the photographs. So we went on the photographs and it was like, hang on, there's nothing on the belt. And that was a bit of an alarm bell. So we're like, oh wow, I wasn't expecting that. And then Oliver, you briefly mentioned, but off the back of that, you went and looked at the whole load and haul cycle. So whilst we were looking at this from a very technical grading point of view, actually you had massive value straight off just by seeing how that was operating. And what I didn't know until it was kind of explained to us by your prime operator is the multi-track system, which does the continuous measurement, only really starts to count as running drives. Is it 4 minutes?
3 minutes.
3 minutes. And you're like, okay, yeah, it's giving you good data, but this is every second. And this is way cheaper than Mortgage. That's not to say that Mortgage hasn't got its place. But we were delighted because it does show that this has got potential to show real value. So as Oliver said, when we first started this, the first thing we were looking at is what is the potential impact on CO2. And Oliver's presented like the national statistics, and we've got various different sources. We built this up. But the big one, if you combine the secondary breakage and everything to do with the blast design in terms of how well fragmented it is, in the UK, we've got almost 43,000 tonnes of CO2 that's targeted, which we potentially could save. But in order to do that, we've got to work with the blasting contractors, and we need to have the right information as the operator to go, right, yes, we need to spend a little bit more money on the drill and blast, and that will see the downstream savings, both in terms of cost, but secondly, in terms of what's that CO2 impact. And that's what kind of excites us, as kind of being completely independent. It's kind of like there's no agenda here. It's like, right, go and do your work, survey it. That's the data that's coming through. And I think that hopefully is going to enable, and I think Oliver's demonstrated, better conversations, more informed conversations within the business, but also, again, with that kind of contractor relationship. So that's, to me, is a critical element, is being able to put some numbers behind this, some impartial numbers. So we've done various other exercises with Tarmac. I'm not going to name the quarries and things, but I'm going to draw on some other case studies that we've been working on using these systems. And one case where we were looking at kind of the extreme end of CO2 impact and cost was where we were highly constrained because of PPV on various blasting, and it was about 150,000 tonnes that we were looking at blasting, and we were able to do a full cost analysis, and I'll show you that in a moment. But basically it said where we were in this stream case that the fragmentation was being really compromised because of PPV, it was costing the operator just north of £2 a tonne. And interestingly, looking at the Mountsorrel stuff, it is, when we start looking at the cost of secondary breakage, it is very expensive when you look at the full mine to mill cost. But not only that, because of the secondary breakage, I mean, your primary that does a drop ball, I think it's using, is it 55 litres an hour? So when you look at the CO2 demand on that, it really is very significant. So it very quickly works up that as a 21% increase in CO2. That's a kilogram per tonne. So it's a big issue and something we need to really look at. Now, in terms of trying to put that CO2 in terms of context, what we've looked at is, let's just take a 1 million tonne quarry and just see what that looks like. So the extreme impact of CO2, and I mean that's right on the extreme end, we're potentially emitting 686 tonnes of additional CO2 that we shouldn't really need to produce. And in terms of contextualizing that, that's equivalent to the kind of emissions of gas and electricity from about 200 households. That's a village. That's a lot of CO2 that we potentially could reduce. Now, that leads us on to the next part of the kind of study in terms of what's causing the poor fragmentation. Now, there's lots of reasons, but I'm just picking out on a couple just to talk through today. So one of the big things we're looking at is the PPV control, and that is where Project Blastwave is really taking off. But I'll just show you some quick examples. So normally when we're dealing with PPV, what we like to do is deck, and either double, triple, in places with quadruple decking, and that massively reduces the PPV. It's not exactly the same as saying it's going to reduce the nuisance impact, and again, that's where Blastwave is taking a deeper look at what's going on there. But it significantly drives up the cost, because once we get into the decking scenario, we're really looking at using the digital electronic decks, and you know, the phenomenal, but it does add cost, so we need to make sure that's properly justified. So once we start in this extreme case, and on this one it was because of a railway line that we were blasting next to, you can see the costs start significantly increasing in terms of the design cost. You know, this one had a really heavy consultant cost associated with it for the controls, third-party controls, and increase in secondary breakage. Now, on this case study, what's interesting is the secondary breakage cost is quite low because it's been offset by a massive increase in the drill and blast cost. So on this case studies, we were then able to basically redesign the whole blast, and we could not only really look at the geology and the impact of the geology, we improved the blast vibration prediction by 131%. We changed how we were actually designing the MIC, so this was looking in more detail in terms of each hole, so limiting it by one hole, limiting the whole blast. And that enabled us to treble the MIC in places. And obviously, trebling your MIC is going to make a big difference on your fragmentation. So that's how that cost saving actually came to light. So that's PPV control. Second thing is timings. Now, I'm not going to go into lots of detail, but I did mention earlier that there was this pioneering work done out in Sweden that we got our hands on. And so these are physically sieved blast piles. There's about 10 of them. And what the author was doing there, to be honest, I think the author had almost a bit of an agenda. I don't think they were really very keen on electronic digital debts. So he did this comparison of using the DigiDets on very short delays against using a non-L on a much longer delay. And what he concluded was the non-Ls significantly outperformed the digital debts. And he's explained here it's a 58% increase in the average size because of the very short delays. Now, to me, that's not actually about electronic digital debts. That is just looking at the timing. What he should have done was then done a digital det at 25 milliseconds. But what this highlights is timings are critical. It doesn't matter what initiation system you're using. So that's what the paper concluded. Because we had access to the data, we could actually then go and do more of a deep dive into this. What the author didn't do was then look at the loading times associated with the non-L and the digital debts. And what was really interesting was the digital debt actually increased or reduced the loading time by 25%. That's massive. So if we then look at it from a cost point of view, you kind of go, actually, there is a place here. Now, that not to say that that's the right solution for every quarry, but what this is really challenging is we need this kind of quality of data to start looking at what is the optimum design, what's optimum timing design, and how it should be initiated. So this is quite exciting because it's a good conversation piece that can come out from this. The next thing I'll talk about is the stemming then. So we've been looking at the stemming plugs, which is distributed by a company called ERG, and these are very stem plugs. So there's been quite a lot of research done in terms of the use of those. And this is some of ERG's material from working in the mines around the world. What you can see here is the stemming plug is to try and produce an airtight gap within the stemming. It improves the efficiency of the stemming, So you can actually potentially use slightly less stemming in there as well. And that shot, that photo kind of speaks for itself in terms of what it can do. They've looked at then using infrared on there to look at the energy escape from it as well. And you can see that the very stem is holding the energy in. And we've done various trials and it has proved a similar thing to what they've published. On here, what they're saying is because that energy is being retained within the hole, you've got more energy going into breaking rock as opposed to being released out the top. So on here, they're quoting at the D50 level at say 45% reduction in particle size, which is massive. Now, what I'm also really interested in is what does that mean for the processing plan? So on here, they're saying it's a 7.8% increase in loadout, which is important, and that's resulting in a 15% increase in output. So those are quite easy things to measure. So that is of interest. Now, in terms of what's happening with these stemming plugs, try to put a bit of science behind it. So this graph is kind of showing what we're expecting to happen on a standard stemming design, that as the bulk initiates, you get a wavefront being pushed out, and that is dictated by the gas pressure. The higher that gas pressure, the higher the VOD, the velocity of detonation. So that should give you more of a shock. In the stemming area, because stemming is not airtight, what we've got then is the gas pressure coming through that stemming. Now, the stemming zone is normally fragmented, hasn't got a lot of weight on it. So as that gas comes in, it can lift it up slightly. Now, as soon as you've got your lifting of your beds, you can't get that vibration energy through there. So you're not going to develop such a strong shock wave to actually fragment it. And I'll show you some videos later of that kind of separating. So if you don't have enough stemming in there, this is when you have potentially rifling, you've got ejection there. And what happens then is you get a reduction in that kind of gas pressure, which reduces the VOD. So you've locked in detonation, your shockwave energy. So the theory behind the stemming plug then is it makes this airtight seal. And in doing so, it gets that gas pressure up to its optimum, increases that shock energy. From my point of view, what also interests me is if it's better able to confine that stemming zone at the top, then we should get more chance of getting shock energy through there, because it's just not letting that gas initially get in there and just lifting the top. So it gives you a more stable column which goes closer to the surface. The other part of this that we're interested in is, again, this comes back to our Project Blast Wave, is looking at the potential reduction in air overpressure. So in South Africa, they have a lot more consistent good weather than we have in the UK. So air overpressure is very difficult to measure, particularly in the UK because of wind. So in South Africa, they've looked at some long-term studies, and they've actually been able to demonstrate that the stemming plug is reducing that air overpressure through the stemming zone, which you would expect if it's operating the way that we think it is. And as you can clearly see here, you've got kind of like a 70% reduction in air overpressure. So this is really exciting, particularly from a nuisance impact point of view. So this is one of the Tarmac stemming plug trials. There's just a video here. And this shot is half and half. You've got one side without the plugs. So the side closest to us has got 2 free faces. That doesn't have the plugs in. The other side does have the plugs in. So arguably, the side with the plugs is more confined. So you would expect better fragmentation on the right. That's the drone survey of the blast. And you can see on the very stem side, it clearly is finer. Now, what we're able to then do is run that through FragMap and really look at the difference between the two sides of the shot. So on here, we're able to measure up to 11% better fragmentation. Now, for this site, there's like a core area where they want it to go through the crushing plan, and it's down to about 100 mil. So we can take an average of what's happening over that 100 plus, and that was about a 7.5% improvement on fragmentation, which is really exciting. So there's more work ongoing with those at the moment, and that's something we're about to start with Mountsorrel. So that's stemming. Now, the next thing what I'm really passionate about is working with the geology, and I think this is something, obviously with my geology background, geotechnical specialist, is something that we're really passionate to kind of bring to the industry, bring to contractors, and just kind of get people more aware about working with the geology. So this is a shot. This is thanks to Bam Riches on this one, actually. This is with Agri Industry. Sorry, Oliver, I've switched over, but it's a really good case study that we got invited in. It was just to come and have a look at what was going on. So on here, we walked onto site, and the first thing we noticed is they were firing completely against the geology, so you get this horrible sawtooth effect. Now, the impact of that means that all the energy from the blast is kind of running down these joints, and it's causing a lot of blast damage, which is visible. But what it's also doing is lifting that stemming zone further back. So when you come to do the next shot, you're not going to get as an efficient shot. So actually, that blast damage is going to impact you not from one shot, but potentially 2 or 3 shots behind you, just because it's giving you this kind of separation. Now, one of the things that we picked up straight away, and it's easy to pick up as a geologist, but you don't see it until somebody shows it, is that underneath the stemming zone, there was actually a shale band, a really fine shale band. And as the shot went off, you can see the air overpressure just lifting off this stemming zone, causing this large segmentation. So in here, what they wanted us to do is have a look at the very stem and see if we could really reduce that stemming length and do it safely, which the very stem did perfectly. However, the problem wasn't to do with the blast design, it was actually the geology. It was down to this shale bed. So let me show you a video of that. So this is the shot going off. So as I said, it's got a very reduced stemming length with the plugs in, and it's held that beautifully. But as you saw that video, you can see the top part of it just lifts off. It's a horrible scenario. This is where you get this kind of horrible stemming zone at the top. And that's why in FragMap, we actually ended up building this kind of 2-tier approach. One is to measure the stemming zone, and the second part of it was to look at the shot. So in here, this is a FragMap. And what we'll do is, you can see the massive oversize on the left, but the actual shot itself was really good. Really fine, good shot. They hit it really hard. But the coarseness is all to do that stemming zone. So that's why we do those 2 independent areas, and then we bring them together to actually look at the whole analysis. There you go. It's like chalk and cheese. When I first did this, most people thought that was 2 different blasts coming together. It's not. It's the same blast. It's quite critical. So sticking with that, we've been working with AI and Tarmac and looking at using drones to do better quality surveying. So this is an independent, it's actually Longcliffe. We've been working with them as well, and this is a blast that we just came and had a look at. We're doing a very stem trial, so flew it and dropped it into Quarry X. But on this blast, and again, as a geologist, these kind of things jump out to me. One is we've got that kind of bedding plane coming through there, and you can really pick that up in the survey. But you've also got a fault running around the back. You can see on the left-hand side, you can see that clay seam coming through. The geology of itself is slightly overturned, and it's not aligned with your face, your free face there. So looking at it, I'm like, oh, I could do with like an extra hole here and just slightly orientate the shot. Really easy to do in hindsight, really easy to do when you've got a degree and 20 years experience working in geology. But these are the kind of things that are actually, we can train people to see these. And again, that's what I'm passionate to kind of pick up. But the real advantage now is, because we've got the high quality drone 3D models, it enables the shot firers now to bring the geology into that blast design and start moving things around to really work with the geology. So this is the video of the blast, and you'll see it go off. So as you can see on the right hand side, you can see things kind of toppling over, massive breakback because we're not quite in line with the geology. You've got things coming in. Now this one, as I said, was done with the very stem, and what we managed to do was reduce the amount of explosives in there quite significantly, because I said, look, the berry stem should hold, it should increase the gas pressure. So on the basis of that, you can reduce the amount of explosives in there. So when this was fired, the first thing is the shot firers were like, has that actually fired? Because they couldn't see it when they were firing it. And the noise was significantly less. So straight off, I'm like, yes, it's done that sealing job. And that potentially has got big ramifications when we're looking at noise impact from blasting. The second thing is when they looked at it, despite having significantly less explosives in there, they were like, for what they're doing, this was way too fine. I'm looking at it going, oh, there's some big blocks in here. No, they're going way too fine. So over and all, when they've looked at the benefit of the berry stem and the amount of reduction of reducing the fines content, so here they don't want to produce fines. They reckon per annum they're able to save something like £800,000, which is really exciting. And what's good for me is that's not consultant led. That is right. Here's some technology. Go and do it. Have a play. You go and do your own analysis. And they've come up with that, not me. I've just kind of pointed them in the right direction. And that's excites me about all of this is enabling the contractor, the operator to use this technology and really enhance what they're offering. And you don't need lots of consultants to come in and pretend to tell you how to do your job. You become the experts of your own quarry. So this is something we're doing with AI. This is Home Park Quarry, and this is basically trying to look at the quality of drone surveying. So we're really keen on drone surveying because it kind of feeds the programs we're using, but also enables us to bring that geology into the design. So working with AI and BAM on this, and I'll show you some of the outputs from here, but this is in QuarryX, so any shot firers on there, you'll be used to QuarryX or a similar program, but that's the kind of quality that we're able to produce. But in there, you can see how much geology we can pick up from that face. So this is one of Tarmac's first plays with QuarryX and drones, and this is just basically just showing a blast design in place. So the next part of it is to look at the real impact of geology. So this is a quarry in Northern England. It's quite a famous one, and it's got some real difficult ground to blast. So I'm going to play a video. This is a blast that we were shown before we got involved, and where I've highlighted, you should see the face is going to move with the blast. So because of this problem, and it's all down to that you've got bedding planes coming through and the very low friction, we were able to kind of bring our geotechnics and geology and integrate it with the in-house blasting team at Tarmac and come up with a new blast design for the quarry to take some really difficult rock out. So this is the video of it going off, and hopefully you can see those beds just completely shunt across. So really quite scary, but you know, well known as this phenomenon in this quarry. So we were brought in because there was a corner of rock, that's a triangle, that needed to come out because it was holding up the development of the quarry. So it's actually that triangle at the bottom of the, I'm just zooming on there. Now the problem with that triangle is when you fire it, all the energy is going to go up the bedding plane. Now historically, up in the back right corner, there was, I think it was 300,000 tons of rock slipped down. It's about 15 years ago. So this is really quite critical. So in here, this is some of our 3D software. I've basically drawn the geology, the geotechnical structure. We brought the blast design in, and that yellow contours, that's the fold hinge. That's how the bed's all folded. So within the house blasting team, completely redesigned the blast. That's the blast of the triangle. And what's really good, from my point of view, you can see none of the faces are moving. So what that enabled us to do was then to have the confidence to go down and take some more rocks. We're actually blasting through these critical beds, and again, just kind of working with the operator on managing how we're going to blast that through. So sticking with the geology then, I mean, that's kind of an extreme case. But what we're able to do is really look at the geological influences on the blast design. So there's lots of components that we do, but I'm just trying to take you through a very quick analysis we did up in Scotland. So the first thing we do is we look at the fracturing within the rock. That's called the fracture network. We make a model of that. We then look at the stresses acting on the rock from the blast design, and then we look at the distribution of those stresses. That then helps us build up like an idealized pattern design, and also what the initiation design is. So this is an example from Scotland that we did, and the BAM riches were firing up there, and the client was wanting to go to a staggered pattern. It was a quartz dolerite quarry. Now, what we did is we built up the geological model, and the contractor was like, look, we do it on a square pattern. We try staggered, it doesn't work. You get no benefit from it. So this is where we set up the kind of geological scene. So take this as like a plan view, just looking down. I've kind of simplified the fracture network. We pick out the critical joints in here, the critical fractures, and these are the two face orientations that we've got. So in this quarry, predominantly work the western face. The north face is just to open it up to make more of the western face, but the north face is horrific. They get really big oversize on it. So we then looked at the stress distribution for the two different faces. And what we identified was on the western face, that it was kind of really did align well with the geology. But on the northern face, you're fighting the geology, which is the fundamental cause of what's going on. That enabled us then to build up stress analysis. And then we can look at that in both compressional and the tensile wave coming back to pick out what's the ideal effective burden and spacing from that. We could then start running various scenarios. So on here, on the left-hand side, we're comparing a staggered pattern against a grid, and actually there wasn't really any difference between the two. So that confirmed what BAM had said. They said it doesn't really change things. Where on the other side, actually there was a big influence. There was a big change whether it was a grid or a staggered. But what we could then do is not only just look at whether it should be grid or staggered, we can actually look at what's the optimum face direction and what kind of blocks we would expect if we rotate that face slightly. So you can see on here, just rotating that northern face very slightly just means you can work with the geology and get that residual block size down. Okay, so I'm going to finish off with a bit of recent work that we're doing with Tarmac, and we're talking to AI supporting on this as well, and that is looking at drones for face profiling. So we've done quite a bit of work with Tarmac over the years, and we developed a safe system work for what we call non-surveyors, but basically quarry managers and shot firers to safely use drones and train them up for face profiling. And what's exciting about this is all the stuff that I'm showing you. You don't need particularly expensive drones out there. This isn't a high cost requirement. So we produced the Tarmac standard, and that got adopted basically by Quinjack. And now you'll see a lot. If you work for Tarmac, you'll pick up the Quinjack stand. You'll see a lot of the words that we put in there as being caught across. But if you're not familiar with this, do have a look at the Quinjack drone standard. There's some good, useful stuff in there. So, because we've got access to some really quite powerful software, what we're able to do is we're able to compare different drone flights and 3D models to see how accurate they are. The software that we run is by MapTech. I think it's about 25 grand, the software. So it's an expensive bit of software that we run. But what that's enabled us to do is working with AI. This is Agri Industries LiDAR scanner. So I think there's a £180,000 scanner sat there, and it can do a very high density profile. So every couple of millimeters, we've got a point on this space, very high precision. But because everything's working off GPS, you can see across on the ground, your perfect alignment or accuracy can't be any better than 2 centimeters, just because that's the GPS error. So the LiDAR scan, everything we're going to say is within 2 centimeters. We then compared that with a standard laser profiler. And because we've got millions of points, what we're basically looking at is 95% of the data. Where does that plot in terms of the accuracy? What falls within it? So a laser profiler on here, that was within 10 centimeters of the LiDAR scan. We've developed a way of kind of flying the face with Tarmac, and AI use basically the same kind of methodology. And when we flew it, we were within 2 centimeters at 95%. So the high quality drone surveys is just as good as the LiDAR scan, which is amazing. So it was really good. And we ran it, the software, through 2 speeds. You can run it through most people use Pix 4D or a similar software. We've got one as well that we work with, that we've written. With that, we ran it on the fastest and on the slowest, and there was only a centimetre difference in terms of the accuracy, which is really important for shot firers, because you need to collect that data, you need to be able to turn it around. So the fast analysis, I think it took 20 minutes to process that through. Now, what this is all leading to is when the drone is not used, flown in the correct way with enough overlap, and it's how stable the flight is in terms of the order you process this with the software. You can get quite poor results out of it. So we audited a couple of different drone surveys with Tarmac done by various contractors and things, and seeing that we've got some significant errors in there. So that's the work that's going on, and the idea is Tarmac are embracing this and now starting to put some quality control in for their contractors, and their in-house team have already adopted all of this. And then, as I said, we're talking to Agri Industries on Friday about kind of similar things. So watch this space. That's coming through. I'm quite excited about that. So that is our hour, because we started at 5 past, so or 1 minute over. But that's our hour's presentation. So I'm going to finish it there. I'll come off, but I think probably just to say thank you for everybody who's managed to join today. It's a pleasure to present to all of you, and thanks for bearing with us.
Thank you very much.